Welcome back. We're down to the last method that we need to write for our binary tries, and that is the add for internal nodes. This is the most complex of the methods that we need to define. And part of the reason for that is because there are actually three possibilities here. And it turns out in order to implement this, we might wind up creating some other methods to help us out. In fact, we almost certainly will. But let's outline kind of the logic of what's needed here. So I said there are three different possibilities. So this is our previous diagram for adding or for building up the binary trie. Let's start a new diagram here. And what I want to do is we are going to assume that we have some internal node that has a number of children. We don't really care too much about the details. We want to look at what the different possibilities are. So this is an internal node. It does have children. I'm not going to bother drawing them all in here. And I guess actually if we're doing the, let's start with this case. If we're just doing the 2-bit version, because 4 would mean that the internal node was full and couldn't have anything else in it. So there are different possibilities. Actually, I guess let's go ahead, blip, blip. And I probably do need some of these just to make sure that this actually makes sense. Okay, so we have our first two children and they have to be full, right? That is a requirement. We wouldn't have added the third unless we had two full children. The last child, though, may or may not be full. Let's just assume that it's not. And remember, these children here, they might not be leaves. This could not be level 1. It might be level 2 or 3 or 4. Could be higher up in the trie. But it kind of doesn't matter, it turns out. What matters is whether this last child is full or not. If this last child is not full, then we have a fairly simple situation where we're going to make a new internal node. So I guess I make a new internal node of the same length, and all the children except for the last child are the same, and the last child gets stuff added to it. And of course, if it's an internal node, it might only be that size. If it were a leaf node, we'd be adding it here. Really doesn't matter, but it is whatever is the new value that has one additional element in it. Okay, so that's option number 1. So option number 1 is our last child has empty space. In some ways, that's almost the easy case. I'll label that A. B. What happens if our last child doesn't have empty space? So let's go back to this original diagram, and we'll select that. Not only is this full, but all of its children are full, etc., etc. So I can't add anything else here. What would I need to do in that situation? Well, in that situation, I would need to add a fourth element here. So my last child is full, but I'm not full, so I have extra space. So what we'd wind up doing is creating a new internal node that has 4, in this case, going from 3 to 4. We have one more than what we had before. It would link to the 3 children that we had before because they are all full, and so we're done with them. And we'd have to create one more. And here again, this could be a leaf or it could be another internal node. If this is at level 2, this also has to be at level 2. So whatever level the children are at, this has to be the same. And we get that picture. So that's option number 2. The situation where last child is full, comma, but current node can grow. Which leaves option number 3, which is this node is full. Okay, so if this node is full, then we'll get rid of the red there. If this node is full, let's go ahead and erase option B and go talk about what happens if this node were full. So if this node were full, it would have another of those, and it would link to here. And once again, if these are internals, they have children going all the way out, and if they're leaves, then it's just kind of what we've shown here with the data. Doesn't matter. The algorithm, what we're going to wind up needing to do is the same. The problem is we can't add here, so we need to have another sibling, and that means we have to introduce a parent. So we are going to create a new node that is one level higher in the tree, and we are going to create a node that is a sibling of this one. So this internal will have another internal, and it might have children underneath it. And that goes there, and that goes there. And of course, in this particular figure, because that can't be the end, we would have to have another, at least one more layer down. And if these were internal nodes, there would be another layer, etc., until we get to whatever level the leaves are at. So that's option 3. Yeah, so those are our 3 possibilities for what is going to happen in this code. Okay, so I've mentioned in this, I've used the expression is full in multiple locations here, and it has empty space. The other way of saying it, last child is not full. And in order to write this function, it would be really helpful if we had a way for our internal nodes, or for actually all of our nodes, whether they are internal or leaves, to tell us whether or not they are full. And so I am going to add in here an is full that returns a Boolean. This isn't really needed by the outside. This is just used in our B vector, so this should be a protected method. And turns out that makes leaf and internal unhappy, but we can make them happy pretty quickly by just adding undefined implementations there. And that will help us with this. So we can flip this around. In fact, I think I will, instead of making this ABC, I'm going to go CBA. So that last case, I'm going to say if is full, and we'll have to figure out how to write that, but we'll come back and do that in just a bit. Else, and that is, oops, that's case A. Else, if children dot last dot is full. That's B. And because we put option A first, we know this node isn't full, so there would be room to grow this. Else, the last child isn't full. Okay, so these are the options that we have. How do we know if we are a full node? We can go ahead and write that, and that'll be the end of this video. Okay, so, well, on a leaf node, you are full if your data length is, and it really would be equal to 1 upshifted bits in alphabet. We've used this in other places. This is how many elements we can store. I have a tendency to use greater than or equal to just on the off chance. Otherwise, you could get really weird behavior if somehow it did become bigger. It's just a habit that I've gotten into to be protective of anything for an upper bound. What about here? Well, the current node is full. Turns out that condition is a necessary condition, so the children's length is greater than or equal to 1 upshifted bits in alphabet. But because we are an internal node, we have children. So you have to be full, or you have to have no more space in you, and your last child has to be full. Because if your last child isn't full, there is technically more space to add stuff. Even though your array is at its full size, there's more place to put stuff in that last child without growing the array. So children dot last dot is full. Okay, that gives us the is full operations, and we will come back in the next video and we'll talk about how to actually implement the code that goes into each of these, because there's another helper method that we're going to have to implement in order to make that work.